Hello, I'm Professor Steve Miller. I'm at the University of Florida Department of Mechanical and Aerospace Engineering, and I lead the Theoretical Fluid Dynamics and Turbulence group. Today I'd like to present a new course, Modeling Inhomogeneous Turbulence with a Historical Perspective. This course focuses on closure of LES, but mainly Reynolds average Navier-Stokes based equations, with emphasis on why the models were created with particular interviews with different authors and review of their articles. On the left, you see the original course flyer, which gives the description and materials and prereqs, what have you. And it was introduced originally as a special topics course in our department. It follows this first course in graduate turbulence. And the reason we created this course is we believe that these skills are really important for researchers in the future. This is one of the most difficult areas of fluid dynamics, and we want to make sure that our students and new researchers are at the forefront of the technology to lead us into the future in prediction and theory, but also have a strong basis on where we were in the past. Turbulence models today are rather rare, and we wanted to make sure that we had an offering here at our university. We also recognize that turbulence modeling is changing today through many empirical approaches that involve big data or so-called AI. We wanted to create skepticism in the class and have skepticism of everything we do in terms of our predictions and how do we know they're right and how the models are right. It's important for all researchers to have skepticism in what they do. Here's the original course objectives, which was printed and will be printed in our future regular offering. And it reads that it's a class that covers in-depth concepts of the science and mathematics of turbulence modeling with a historical perspective. And we try and give as many examples as possible involving contemporary approaches. And all these topics are related to turbulent flows that we observe in our daily lives and in the field of engineering, and in particular aerospace engineering. Much of the class is mathematical review in the beginning and statistics, but we quickly move into the different models and end with LES closures and some special topics. We delivered the course in person and also recorded it, and this lets an international audience also view the course for free. They would also be given a complete set of notes, which I was able to develop for the course, mostly in advance. During the class, we reviewed about 20 articles, which are all the original articles that introduce models, plus some other important papers that introduce important theory and experiments. All this was integrated through the course in a 4-part computer project, which I'll show in a couple minutes, where we implemented a simple turbulent boundary layer solver using a RANS closure. We also had the students write a term paper on a topic of their choosing and give an overview presentation at the end of the semester. Course material took a lot of time to put together, and it was based on multiple turbulence books. And the course material in the handout is not just completely given to the students. It's actually a LaTeX set, but we blank out certain parts of equations and sentences. And so when we go through it, we actually develop those math in class and explain how those equations come from. This was recorded and put online, and so that way students could also grab the course packet and follow along a line at their own leisure. For example, in this slide on the left, we have the student handout screenshot from Cebeci-Smith model for coefficients of momentum transport. On the right, you see my own handwriting, which was screen captured from the recording. I mentioned that we looked at a number of articles and models. Beyond the general articles on statistics and basic flows that are used for calibration and formulation of turbulence models, we reviewed these key models on the right, which should be familiar to many people. And we captured the original journal paper and shared it with the class, and we actually criticized and read the article in class, and also talked about its major findings and equations and how they fit into contemporary approaches. Also trying to understand why the original papers were written for particular cases, and where those authors were, and what probably inspired them. We also looked at a computer project. As I mentioned, it's a 4-part project. In the first part of the project, we look at Lorentz flow and try to reproduce the chaotic nature of the flow and demonstrate to students that it's generally easier to predict statistics than it is deterministic nature of flows. Then we created a basic parabolic marching solver solving just a basic PDE, which is representative of a more complicated PDE relative to boundary layer equations. Then we extended that solver to the laminar flow, and finally we extended it to the turbulent flow. Here are some screenshots from the first computer project. It's based on Lorentz paper in 1963. And the idea is that we reproduce the time domain predictions of Lorentz. So this is an important lesson for the students, that when we change initial conditions, later conditions can change a lot. Part 2 solved the basic equation du dx minus d2u dy2 equals 1, and they compared that numerical solution to the analytical solution. Why did they do this? So they could get their compilers and programs up and running and get a basic solver which will modify for the laminar flow. We take this equation on slide 9 and work on computer project number 3 to produce a laminar flow in a channel in 2D. So now we have a continuity and momentum equation, introduce the viscous coefficient. And you can see how the equations in part 2 and part 3 are related. Averaging the variables and adding in a eddy viscosity, and we used the Baldwin-Lomax model of 1978 to do that. It's pretty straightforward, and almost all the students were successful in completing this part of the computer project. Here, the equation you can see has an eddy viscosity added to it. And in the lower right, we have student examples where we have the log law, the wall, the viscous sublayer, and an outer layer. The x-axis is the inner coordinate, and the y-axis is a non-dimensional velocity. So through this approach, we're able to show students how to completely create a code from scratch and implement one famous turbulence model. Students did suggest that they would want to implement other models through the class, which are maybe one equation model. The students were asked to write a term paper and presentation through the class, and they could choose any topic on turbulence they desire, and they would have to present it in a short 10-minute presentation at the end of the class. Students were required to peer review papers and, of course, critique the presentation, which goes into like peer review grading. This way they all had some insight and skin in the game, if you will, in terms of the presentations and improving writing. We followed the NASA writing guide to try and guide their writing style and improve technical writing. A huge part of the class was the historical perspective. In the lower right, you see some figures of, say, Lomax and Baldwin, and we were able to reach out to some of these turbulence researchers and understand why they created these models. In particular, I wanted to present the class through like an interview, some thoughts like who created the models, why did they create them, what was their environment they were in when they did, what problems were they trying to solve, which is always interesting because the problems they were trying to solve aren't always the ones that we use their results are for today, and what was the impact in their opinion of their models. Student outcomes is important to measure when developing new classes, and we use the university's statistics and evaluation system, which is presented at the end of every course. These particular questions were course-based questions, and it's on a 1 to 5 basis. Where the students are divided into sort of bins, 1 to 5. 5 is the best rating and 1 is the lowest. So most students gave us most counts in 4 or 5, which is positive. We also gathered some direct comments from the students. They can be pretty lengthy, and I screenshot a few to present here. But generally they were positive, and we're using their feedback to try and improve the course and offer it on a permanent basis every 4 semesters. The major outcome from the class, of course, is that we're making it permanent and offering it 4 semesters, but we're also posting all this information online, and you can use the QR code generated by Google on the left, which will lead you to the course homepage, which is on my personal page, saemiller.com/turbulence-modeling. Or you can go directly to the YouTube playlist, which is the link on the bottom. So this is, of course, Reynolds' experiment in there in the early part of the class. There's currently about 43 hour-long lectures approximately online, which includes discussions of the computer projects. And in the future, we hope to add more as we expand the course and try and make it understandable for a global community. Thank you very much for your time today, and I'll take any questions.